Hello everyone, in this video we'll be talking about the definite integral. So if you remember last time, in the last video, we integrated, or we found the quote-unquote area, or distance of this guy, some velocity function, and we got a negative number. And I said it wasn't the area or the total distance traveled. Remember, if we wanted to find the total distance, we'd actually need to take the speed function and find that. So we'd have to integrate this from 1 to 2 dt. And that would give us the total distance traveled. But it did have a meaning. And it was kind of the net distance it traveled. So given the number line and a 0 marker, we started somewhere and then we kind of meandered up and then back down, and we ended to the left of the 0 marker. And that kind of gave us the total displacement from 0 that we traveled. And we're going to formalize this now into the definite integral. So what is the definite integral? So our definition here is that the definite integral of a function f from a to b, we write that as the integral from a to b of f of x dx. And that is equal to the limit of f of x sub I delta x, just like when we were figuring out area. But we can expand out what x sub I is. It's just some x value in the ith interval. And delta x is still the same b minus a over n. So before we get into the first example, I want to go over some notation. So this thing is creatively called the integral sign. Right? The thing inside here is called the integrand. And this is called our lower limit. This is our upper limit. Okay. And we can kind of see some parallels here. So the a and b kind of get absorbed into this delta x. And this dx actually becomes delta x. So as delta x gets really, really small, the delta just becomes a d. And the f of x is transferred to f of x sub I. So let's go ahead and look at a simple example. So we're looking at the integral from 2 to 3 of x minus 1 dx. So just by definition, this is the limit of the sum of x sub I minus 1 times 3 minus 2 over n, right? Because it's b minus a over n. Now, what can this x sub I be? Well, we can partition this into, we're only going to do a few partitions here. But this is partition 1. This guy's partition 1. This one's partition 2. This partition 3. This partition 4. So x1 lies anywhere in here. So maybe this is x1. And x2 is right in the middle. x3 is a little bit to the left. And x4 is the right endpoint. And this guy, the limit as n goes to infinity of the sum from 1 to n of f of x sub I delta x, has a very special name. It's called the Riemann sum. Okay. It's called the Riemann sum because of Bernhard Riemann, who actually developed this method for finding areas. So that's it. He was important enough to have this named after him. So that's the Riemann sum, and the idea here is that x sub I is just anywhere in this interval. So these actually aren't x sub I. This is f of x1, f of x2, f of x3, and this is f of x4, where x1 is right here, x2 is right there, x3 is right here, and this guy right here is x4. All right. So it's important to note that when we're talking about area in these particular instances, we're not talking about just a positive area. We're talking about a signed area. So what does that mean? That means that if our area lies completely above the curve, like in these two green areas, then these are positive. There's a positive area and it's a positive area. And if it lies below the curve, like this red region here, or pink region, I'm not really sure how it translates. This is a negative area. So if we were to label this function f of x, the integral from a to b of f of x dx, if we were to call this area 1, area 2, and area 3, this would be area 1 minus area 2 plus area 3. So we're taking this region here and this region here. Since they have positive area, we just add them together. And then we take the area here, and since it's below the x-axis, we just subtract it off. Okay. So what does the definite integral tell us? It tells us the net area, right? So if we are looking at the areas here, we're taking this guy, and then we're going to subtract the actual value of the area, which will be a positive value, and we're going to add this area here again. So the total area, to reiterate, is going to be the greens minus the reds. Okay. So if we were to look at an example here of, say, a function that starts up here and goes down, this is a, and then we have a semicircle here, and then we kind of go down, and then we go flat. And we end here at B. Okay, well, what are we going to add? We're going to add this area and the area of this semicircle, and then we're going to subtract this triangle and this rectangle. And so if this is our function f of x, the integral from a to b of f of x is going to be the area of the first triangle, so we'll call this T1, plus the area of the semicircle minus the area of this triangle, T2, minus the area of that rectangle. And if we make this even more concrete, let me zoom in here. Say this was 1 to 3, and this was 3 to 5, this was 5 to 7, and this was 7 to 9. The area here is going to be, let me find some room. I'll just clear this off. Okay, it's not letting me clear it off. So we'll just ignore this for a second, and we'll say that the area of triangle 1, well, it's 1/2 base times height. So we're going to need some heights here. So let's say this is -2 on the bottom, and we'll say it's 3 on top. So it's 1/2 times the length of the base, which is 2, times the height, which is 3. And the area of the semicircle is 1/2 pi r squared. So we need the area here, or the radius. And if this length is 2, then the radius is 1. So this is pi over 2. And the area of the second triangle, well, our base here is 2 again, and our height is also 2. So it's 1/2 2 times 2. Oh, the area of T1 is 3, and the area of T2 is going to be 2. And the area of the rectangle is just base times height, so the length is 2, and the height is 2, so that's 4. So we plug that into the formula. It's 3 plus pi over 2 minus 2 minus 4. And so it's 3 minus 6 plus pi over 2. So that's pi over 2 minus 3, which is equal to the integral from 1 to 9 of f of x dx. Okay, so now that we know how to take an integral, let's talk about when we can actually do it. So, when can we actually integrate a function? And the big principle here is we can integrate a function. So we can integrate integral, say, from a to b of f of x dx if f of x has finitely many discontinuities. Okay, so an example of this would be something that you can integrate, so from a to b. Something you can integrate here is maybe f of x loops up like that, and then there's a jump discontinuity, and then we have a hole, and then another jump discontinuity, and then we go down to b. So since this has 3 discontinuities, one here, we'll call this C1, we'll call this hole C2, and we'll call this hole C3. And it has finitely many discontinuities, so we can break it up over these discontinuities and actually figure out what the integral is. So in this particular case, the integral from a to b of f of x dx, we know from last time that the area of the whole is equal to the sum of the area of its parts. So it's the integral from a to c1 of f of x plus the integral from c1 to c2 of f of x plus the integral from c2 to c3 of f. And I'm going to slide all this over. I guess I'll slide the y-axis over too. Plus the integral from c3 to b of f of x. So if it has these finitely many discontinuities, we can actually split it up. But there are instances where we can't split it up. And let's look at an example where it's actually not integrable using the calculus techniques that we're going to learn in this course. So for a non-example, we can look at the function f of x is equal to 1 over n when on the interval. So our non-example here is f of x is 1 at x equals 0. And then it is n for x in the interval from 1 over n plus 1 to 1 over n. So if n is equal to 1, then we're looking at 1 between, let's see, if n is equal to 1, then x is between 1/2 and 1. So 1/2 and 1, and that's a 1 right there. And then for n equals 2, we're looking at the interval from 1/3 to 1/2. And there it's going to be 2. So it's all the way up here. And then for n equals 3, we're in the interval from 1/4 to 1/3. And it's going to be all the way up here. And it's going to continue, and this thing is going to grow infinitely. So there are infinitely many discontinuities. And how many? As many as there are integers. So in particular at 1/2, 1/3, 1/4, and so on. And this is not Riemann integrable. We might be able to find a different type of integral, but that is beyond the scope of this course. So now we know when things are integrable. So I'm just going to write here, this is not integrable. Okay. So now that we have an idea of what the integral is and when something is integrable and the formula for it, let's do an example. But before we start the example, we're going to talk about the midpoint rule. So as we know, the integral from a to b of f of x is equal to this sum of f of x sub I delta x, where this is any x value in the ith interval. Okay, so that means we can pick anything. And what we're going to do, as is stated in the midpoint rule, we're just going to pick the midpoint of these intervals. So if I break up a to b into fairly even parts, our x1 is going to be right here, our x2 is going to be right here, x3, and so on. We're just picking the midpoint of it. And if we have a function defined on that interval, we're just going to make our rectangles from the midpoint up to the next midpoint. And that's it. And x sub n is going to go to whatever the previous midpoint was. Okay, so the formula for this, our delta x is still the same. That's still b minus a over n. But our x sub I is going to be a little bit different. And we can go through how to figure out what the midpoint is, but knowing what it is kind of unimportant. It turns out that x sub I, in the textbook I am currently teaching from, they call x sub I bar. So I'm going to put a little bar over it. and it's 1/2 times x sub I minus 1 plus x sub I. And the important thing to know here is that this is the midpoint. These are all bars. It's the midpoint of the interval of, in particular, the ith interval. And we would just use the formula the exact same way. The other one that we normally use is the Wright-Riemann sum. Okay, so if we're given a similar function, this is f of x, we're on this interval from a to b, and we partition it, we're just going to pick the right endpoints. And so it's the exact same thing as the area formula that we did last time. So it's not nearly as complicated. Okay, so let's look at an example. So we're going to find the integral of 1 over x dx using 5 partitions, using both the midpoint rule and the right endpoints. Since delta x is the same for both of them, I'm going to write it up above before I even start a or b. So delta x we know is b minus a over n. So this is 2 minus 1 over n, or 1/5. And now we can figure out what x sub I is, and then once we figure out what x sub I is, we can use the midpoint formula to figure out what those x sub I bars are. So x sub I, remember, is a plus I delta x. So it's going to be 1 plus I over 5. Okay, so now that we have that, our midpoints, well, remember it's x sub I minus 1 plus x sub I over 2. So this is going to be 1 plus I minus 1 over 5 plus 1 plus I over 5 all over 2. And we can clean that up to be 2 plus I minus 1 plus I over 5 all over 2, which is going to reduce down to 1 plus 2I minus 1 over 10. Okay. So now using the midpoint rule, we have our sum as I goes from 1 to n of f of x sub I bar delta x. Okay, we can just plug it in now. Remember that f of x was 1 over x. So this is the sum as I goes from 1. We know n is 5. 1 over x sub I bar times delta x. Plug in what x sub I bar is. Maybe let's clean that up a little bit more. This is 10 over 10, so this is 2I minus 9 all over 10. We take the reciprocal, it's 10 over 2I minus 9. And delta x is still 1/5. Okay. So this, we just plug in I equals 1, 2, 3, 4, and 5. So we have, and we can pull this, we can actually simplify this a little bit more. So the 10 and the 5 reduce to a 2. That's a constant. We can pull it out. So this is 2 times the sum from 1 to 5 of 1 over 2I minus 9. So it's 2, and then we're just going to figure out what this sum is. So when I is 1, it's just 2 minus 9. When I is 2, it's 4 minus 9. When I is 3, it's going to be 6 minus 9. When I is 4, it's 8 minus 9. And when I is 5, it's going to be 10 minus 9. Okay. So this is 2 times negative 1/7 minus 1/5 minus 1/3 minus 1 plus 1. So these cancel out, and we have negative 2. Let's get a common denominator here. So 7, 5, and 3 are all co-prime with each other. So the least common denominator is going to be 7 times 5 times 3. So 7 times 3 is 21, times 5 is 105. And 7, or we just need to multiply it by this guy, by these two multiplied together, this by these two multiplied together, and this by these two multiplied together. So it's going to be 15 plus 21 plus 35, all over 105. So this is negative 2 times 15 plus 35 is 50, so that's 71 over 105, or negative 142 over 105. Okay, now this seems a little strange to me. I'm sure there's an error here somewhere, because 1 over x is positive throughout the entirety of 1 to 2. Or, yeah, 1 to 2. So there's a negative that I missed somewhere and carry throughout the whole thing. But you can go back and check to see where the mistake is and leave it down in the comments. But moving on to the right rule, the right Riemann sum. This is a little easier. So we know delta x is 1/5. And x sub I is just the right endpoints. So it's 1 plus I delta x, or 1 plus I over 5. So f of x sub I is going to be, well, let's clean this up. This is 5 plus I all over 5. And when we take the reciprocal of it, this is 5 over 5 plus I. So our sum, remember we're using 5 partitions. So f of x sub I is going to be 5 over 5 plus I times delta x, which is 1/5. And this guy, we can reduce. These two go away to a 1. And so this is just the sum from 1 to 5 of 1 over 5 plus I. And this is going to be, when we write it out, it's going to be 1/6 plus 1/7 plus 1/8 plus 1/9 plus 1/10. And we can do the same thing and get a common denominator and then add everything together. And the common denominator, well, this is 3 times 2. This is just 7. This is 2 to the 3rd. This is 3 squared. And this is 2 times 5. So our least common denominator is going to be 8 times 9 times 7 times 5. which is kind of a big number. So we're just going to leave it like this. Okay, so those are examples. Just going to look back really quickly. Oh, this should be a plus 9. That's the error, right? From here to here, it should be a plus 9. And so that's going to change all of these to pluses. Plus, 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 plus. And that will change our formula dramatically. So we're going to get 1/11th plus 1/13th plus 1/15th plus 1/17th plus 1/19th. And now it really becomes pretty unwieldy, and we'll just leave it like that and get rid of the rest here. And that was the error. It was just an arithmetic mistake. Okay, so when would we want to use the midpoint rule over the right-hand rule, over the left-hand rule where we just pick the left endpoints instead of the right endpoints? And it depends essentially on the function. Sometimes picking the left endpoint's just a lot easier. Sometimes picking the midpoint's a lot easier. Sometimes picking the right endpoint's a lot easier. But all these exist, all these work, because as we take the limit, the midpoint and the left endpoint and the right endpoint all kind of shrink to the same point. So it doesn't really matter in the end when we actually take the limit. So finally, we're going to look at some properties of the definite integral. Okay, so the first property that we're going to look at here is the integral from a to b of f of x dx it answers the question, what happens if we switch the upper and lower bounds? And it turns out that it's a negative. And this is kind of complicated to show, given what we have right now. But next time when we talk about the fundamental theorem of calculus, it'll be a lot easier to explain. So we're going to hold off on the explanation for this. Okay. The second thing is that it answers the question, what if we're integrating from something to itself? So we have a function and we have a. And we're integrating from a to a. And so this integral from a to a of f of x is going to be the sum of f of x sub I delta x sub I. And delta x sub I is a minus a over n. So this is 0. So we're adding up 0 plus 0 plus 0 and so on. So our final answer here is 0. Okay. The third property is going to be, what happens if we integrate 1 dx, which is the same as integrating just dx. And the answer here is, I think it's a little clear, but we're going to just really make sure we understand it. So if this is 1 and we're integrating from a to b, what we want to do is find this green area right here. Okay. And as we can see, this area is a rectangle where the height is equal to 1 and the base is b minus a. It's the length of the interval. So the area is equal to b minus a times 1. So this is just b minus a. Okay. So our fourth property here is that the integral from a to b of c times a function is going to be c times the integral of that function. Okay, and this comes from the definition using the sum. So the left-hand side is going to be c f of x sub I delta x. And this is from 1 to n. So this is c f of x1 plus c f of x2 plus c f of x3 and so on to c f of xn. We have that common factor of c, so we can factor it out. And we get c f of x1 plus f of x2 and so on to f of xn. And this guy is just the sum of f of x sub I delta x as I goes from 1 to n. Now that we have this all written out, let's take the limit. We'll take the limit here, and the limit here, and the limit here. And as we know from basic properties of limits, we can take the constant and factor it out of the limit. So this is c times the limit as n goes to infinity of the sum of f of x sub I delta x, which is, by definition, the integral from a to b of f of x. So we have a really nice property here. This is kind of a combination of the integral from a to b of dx and the integral of c f of x. These two combine and tell us that the integral from a to b of c dx for any constant c is just c times b minus a. Okay, next, these are all coming from properties of sums, and we are on property 5 now. So property 5 says that the integral of f of x plus or minus g of x is going to be the integral of f plus or minus the integral of g. And those are our big 5 properties here. There is another property that is kind of important, and we touched upon a little bit. If c is in this interval from a to b, then we can split up the integral. So the integral from a to b of f is equal to the integral from a to c of f plus the integral from c to b of f. Okay, so let's draw a picture, kind of see what that looks like. So if this is a, this is b, and we have some point c here. And this is our function f of x. So what we can do is we can split our integral up over c. And this is the integral from a to c. And this guy over here is the integral from c to b. So this is the integral from a to c. This is the integral from c to b. And so the integral from a to b of f is equal to the green plus the red. Okay. And these are basic equality properties for integrals. There are a few more properties, and we're comparing them. So we're going to take some comparison properties of integrals. So let's compare integrals with other integrals and see if we can figure out a bound on the area, on this net area. So if I have a function f of x on an interval, okay, so I'll draw it out here. Here's a, here's b, and we'll have f of x here, bounded. Okay, so I'll have a function f of x, and I'm not going to draw it because I'm going to draw something else. And I have another function, g of x, that's defined on the same interval. Okay, so the first thing we can notice is if f of x is greater than or equal to 0 on this interval from a to b, then the integral from a to b of f of x should also be greater than 0. And it makes sense because since the whole thing is above 0, this area is never dipping below the line, so we're never going to have anything to take away. Similarly, if f of x is less than or equal to 0 on this interval, then the integral from a to b of f of x should be less than or equal to 0. Okay. For our third property, if g of x is greater than or equal to f of x for every x in this interval that we're looking at, then the integral of g is going to be greater than the integral of f. Okay, and we can see that if g is bigger than f, then f is less than g. So we can just flip everything around and get the other inequality here. And the last comparison property here, we're going to get rid of g, is we're going to notice that f on this interval is kind of bounded above by something, and we'll call this big M. And it's bounded below, well, by 0, but anything really less than f of a in this case. And we'll call this little m. And if we look at the areas here, the area of M completely encompasses the area under the curve. And the same thing with this little m, the area under the curve completely encompasses this pink area here. So we have some nice comparisons to solid bounds, and we can actually get really easy numbers with it. So the property is that if little m is less than or equal to f of x, is less than or equal to big M for every x in the interval from a to b, then using property 3, the integral from a to b of m, little m, is less than or equal to the integral from a to b of f is less than or equal to the integral of big M. But little m and big M, they're just numbers. So we can apply one of the earlier properties here, and we can get m times b minus a is less than or equal to the integral from a to b is less than or equal to big M times b minus a. And this ends up being really important in a lot of applications where you don't know the exact value, but you can get two really close things to approximate the actual value of the integral. So that's pretty much it for this video. We can do one more example before we end. So we'll look at the integral from a to b of 3x dx, and we'll actually pick values for a and b. We'll pick 1 and 7. So we haven't gone through a nice, easy way to do it, so we're going to have to do it the hard way. But let's go ahead and graph this. So we know that when x is 1, y is 3. And when x is 7, y is 21. And we know it's a straight line here. So this is 1. This guy down here is 7. Okay. We can find the area without using the Riemann sum. Because what we have here is we have a triangle and we have a rectangle. And so the area is going to be the area of the rectangle plus the area of the triangle. And we know what the area of the rectangle is. It has a base 7. It has a height 3. So the area of the rectangle is 21. And then the area of the triangle is 1/2 times the length of the base. It's not 21. From 1 to 7, we have 6. So it's 6 times 3, which is 18. And it's 1/2 base times height. So the length of the base is 6. And the height of this is 21 minus 3, which is 18. So this is going to be 18 plus 3 times 18, or 4 times 18. And we can just do that on the side real quick. 18 times 4, that's 32. So that should be 72. Now, we want to confirm that property 4 holds here. We want to confirm this. So let's pick our lowest possible, or our biggest possible lower bound here. And everything on this interval from 1 to 7, our function lies below, or lies above the line 3. So while we can pick anything less than 3, less than or equal to 3, let's pick m equals 3. And similarly, we know that on the interval, our function doesn't go above 21. So let's pick big M to be 21. Okay, so little m times b minus a is going to be 18, right? It's 3 times 6. And big M is going to be 21 times 6, which is, what's that, 126. And that is definitely containing 72. So it checks out. All right. So that's it for today's video. To recap, we talked about the definite integral. It's okay to have negative values because we're looking at a net area or a net displacement. And We talked about how the definite integral is just the Riemann sum, but we can pick anything in the ith partition. One particular thing is the midpoint. We can also pick the left and right bounds. And then we talked about a bunch of different properties of the definite integral. So next time we'll be talking about the fundamental theorem of calculus, and we'll go back to showing that the integral from a to b is equal to negative integral from b to a.